Hello and welcome to our webinar. Today we will give a brief introduction to NeoFS and show how to start using it. At first, let us introduce ourselves. We are Neo St. Petersburg Competence Center, NeoSPCC for short. We are a research and development company based in St. Petersburg, Russia, founded in July 2018 with support from Neo Global Development. Now we are a team of 12 members working on Neo software ecosystem projects and Neo blockchain itself. Our core project is NeoFS. It's a distributed decentralized object storage integrated with Neo blockchain. Nodes are organized in a peer-to-peer network that takes care of storing and distributing users' data. Any new user may participate in the NeoFS network and get paid for providing storage resources to other users, or store his data in NeoFS and pay a competitive price for it. Since anyone may participate in NeoFS network, we need a reliable mechanism to ensure users' data consistency and availability in a chaotic environment. To achieve this goal, we use a combination of homomorphic hashing for data integrity checks and game theory models to create a situation where all nodes behave correctly and the data is stored safely. The decentralized nature of NeoFS eliminates not only the centralized points of failure, but also centralized points of control. In NeoFS, we try to shift as much power to user side as possible. Only users have full control over the data, where, how it's stored, and who can get access to it. Unlike many other projects in this area, we are not trying to create a parallel reality in a technological sense. We understand that for solving real-world problems, we need to use standard protocols and have ability to integrate NeoFS with existing systems. There are protocol adapters or gateways that allow access NeoFS via standard HTTP or S3 protocols. Users can develop their own gateways to integrate NeoFS with existing systems they are using, like accounting system, CRM, or maybe a corporate backup system. Now let's dive a little deeper into technical details. NeoFS network nodes run the same software and communicate by the same protocol, but may have different roles. There are regular storage nodes that store data and process user API requests. They form the outer ring. There are also nodes that take care of network health and perform service tasks like data audit and payment settlements. Such nodes form the inner ring. There are not many of them, and they use DBFT 2.0 consensus algorithm to coordinate their actions. Inner ring nodes are connected to Neo blockchain and are constantly monitoring events coming from it to synchronize the state and the state of NeoFS smart contract that manages users' money deposits and information about inner ring nodes themselves. Since inner ring is a critical infrastructure part, not every node may get this role. Nodes willing to become the inner ring node should be registered in NeoFS smart contract in the Neo blockchain and pay some security deposit that will be lost in case the node starts to behave incorrectly. In addition, in the same way as Neo consensus nodes, NeoFS inner ring nodes try to achieve maximum possible geographical, political, and network decentralization. The main use case for NeoFS is decentralized applications data storage and content distribution. Currently, most dApps do not store their assets in a decentralized fashion, which makes them not really distributed applications. With NeoFS, dApps can upload contents to NeoFS and distribute it to clients via protocol gates using standard HTTPS protocol, or for example using NeoFS API from mobile applications. Moreover, dApps can access NeoFS directly from smart contract code. For example, dApp smart contract can generate some data like hilarious cat picture and put it into NeoFS rather than storing it in the blockchain. Storing data off-chain would be significantly cheaper and easier to deliver to client. As we mentioned before, inner ring nodes monitor state of NeoFS storage nodes. Using this information, they maintain up-to-date network map. It's a multidimensional graph where nodes have attributes and are grouped by those attributes and their values. This allows us to use a special data placement function to find nodes that would store an object when we want to put it into NeoFS network or to get it. This approach allows not to have any centralized metadata storage having object locations and not to rebalance data with every joining or leaving storage node as it happens in DHT-based systems. Like files in file system are organized in directories, objects in NeoFS are organized in containers. Each container is served by a subset of storage nodes that satisfy storage policy defined for this container by the user. To calculate that node subset, we apply storage policy filters to network map. The resulting set of nodes will be responsible for making sure that storage policy is satisfied and data is not corrupted. If they do it, they will share users' payment for the data storage. One storage node may serve many containers, so if it behaves correctly, small shares from each container will sum up in a significant reward. The same is true for the losses in case of containers nodes misbehavior. This motivates node to keep an eye on other containers members and properly perform all required replication, migration, and data recovery processes. The other non-obvious benefit of this approach is that the bigger the NeoFS network grows, the more stable it becomes, because the chance of network changes would affect the container are decreasing with the increasing number of nodes in the network. It means, unlike in DHT approach, the amount of data migration we need to do decreases with the network growth. When you have a large number of objects in a distributed network of untrusted nodes with an ever-changing topology, you can't use classical approach with comparing object hashes with some sample in the centralized metadata storage. That would cause unacceptable overhead. To solve this problem in NeoFS, we use homomorphic hashing. It's a special kind of hashing algorithms that allows to compute the hash of a composite block from the hashes of the individual blocks. For integrity checks, NeoFS calculates a composite homomorphic hash of all the objects in a group under control and puts it in a structure called storage group. During integrity checks, NeoFS node can ensure that hashes of objects stored are correct and are part of that initially created composite hash. This can be done without moving objects' data over the network, and no matter how many objects we have in a storage group, the hash size will be the same. So how does NeoFS ensure data is not lost or corrupted? Each epoch in ring nodes perform data audit. It's a two-stage game in terms of game theory. At first stage, we ask nodes in a selected container to collectively reconstruct a list of homomorphic hashes that would form a composite hash stored in a storage group. By doing this, nodes will show that they have all objects and are able to provide a hash of those objects. We can validate provided list of hashes, but at this stage, we do not know if some nodes are lying. At the next stage, we need to make sure that nodes are honest and don't fake check results. Inner ring nodes calculate a set of node pairs that store the same object and ask each node to provide 3 homomorphic hashes of this object. Ranges are chosen in a way that a hash of a range asked from one node would be the composite hash of ranges asked from another node in that pair. Nodes can predict objects or ranges that would be chosen for audit. They can't even predict the pair node for the game. This stage will disclose malicious nodes very fast, because each node is serving multiple containers and storage group and participates in many data audit sessions. When node is caught in a lie, it will not get any reward for this epoch, so the price of faking checks and risks are too high, and it's easier and cheaper for the node to be honest and behave correctly. By combining the fact of nodes being able to reconstruct the storage group's composite hash and the fact of nodes' honest behavior, the system can consider that the data is safely stored, not corrupted, and available with a very high probability. For incentive model and pricing, we implement a free market. Each node declares how much it wants to receive as a reward for data storage service for the upcoming epoch. Placement function considers the declared price and prefers nodes with better prices. However, because nodes in network map declare key value attributes describing their parameters like geographical location, type of storage, capacity, and other things also used in storage policy, it leaves room for nodes that want higher price but having better or unique services to still get into the placement function result. In short, if you are too greedy, you will not get users and will not get rewards. To have higher prices, you need to satisfy market's demand or provide something unique. As you can see in the example graph of price to capacity change, node needs to keep price in the market to get most profit. This should guarantee the competitive price for data storage in NeoFS. But how does the payment for storage happen? NeoFS uses gas for all payments. To be able to pay for storage services in NeoFS, one has to deposit some gas to NeoFS smart contract address. This event will be monitored by in-ring nodes and reflected in user's account balance internally in NeoFS. NeoFS in-ring nodes keep track of all accounts using NeoFS and using DBFT consensus algorithm, the same as in Neo blockchain, agree on users' mutual settlements, rewards, distribution between nodes owners, and other payment-related procedures. For example, some person may own few storage nodes and provide storage services, but at the same time use NeoFS for storing his backups in different geographical locations. In this case, rewards from his storage nodes may be used to pay for his backup automatically without transactions on main Neo blockchain. But it's also possible to withdraw the gas accumulated inside NeoFS to Neo blockchain address. To do it, user has to issue withdraw call to NeoFS. In-ring nodes will log the desired amount and issue a check signed by all in-ring nodes. Then, user has to invoke NeoFS smart contract, providing it with this check. If it will be verified successfully, smart contract will send gas to user's address, and in-ring nodes will reflect those changes in the internal account balance. If check is not used during validity period, gas locked for withdrawal will be unlocked, just like in the real world. In the beginning, we mentioned that NeoFS can be accessed directly from smart contract code. This feature becomes available in Neo 3.0 release with introduction of Oracle's protocol. Smart contracts will be able to issue GET and PUT request, and it should be cheaper than storing data on-chain. To interact with existing systems using standard protocols, NeoFS has protocol gates. Gates are mainly maintained by users and are not part of NeoFS network. From the start, we provide HTTP protocol gate that will allow access data from NeoFS using regular browser. Later, we plan to release AWS S3 and OpenStack object storage gates to allow more sophisticated integrations. Technically, one may easily develop own gate by using NeoFS protocol libraries. Combining those properties, we believe NeoFS will help dApps to become more distributed by using decentralized system for data storage and content distribution. Also, we look forward to enabling already existing systems with decentralized storage. In our vision of the future, NeoFS is just a first step in our journey to the true cloud platform. Right now, dApps are very limited in storing and manipulating data, and we want to solve this with NeoFS. Next, we want to allow dApps to offload heavy computations to NeoLambda, a specialized decentralized network that will execute code off-chain but with comparable level of trust. NeoLambda will be able to run code close to NeoFS storage. At the first stage, it will allow to run stateless handlers, but later, this will serve as a base for implementing distributed stateful transactional data processes. As a result, it will be a fully decentralized stack of tools and technologies, allowing to implement almost any existing test on top of it. We think of it as a true cloud platform, the base for next generation of distributed applications. And now, few announcements. On September 3rd, we released a local NeoFS SDK. It's a set of Docker containers allowing to set up fully functional NeoFS network deployment on developer's computer. It's mainly targeted for integration testing and new NeoFS application development. Next, we are launching publicly available NeoFS network testnet. At first, it will be connected to private deployment of Neo blockchain for testing purposes. At the beginning of 2020, we will deploy NeoFS network into Neo 3.0 testnet. Stay tuned!